Hello students, welcome to our channel Helm of Science. In the previous class, we had a preliminary discussion about the structure of atom and the various experiments that are performed by Sir Rutherford and Niels Bohr, and we also discussed about the stability of atom and the atomic number and mass number. Today, the topic that I will be discussing is about the arrangement of electrons in the atoms, right? So, arrangement of electrons in the atoms. Okay. Now, we know that electrons are negatively charged particles. That means they carry negative charges. Now, as the electron moves around the nucleus, they form a cloud of negative charges, right? And this cloud of negative charges, they revolve around the nucleus in certain energy levels. Okay, so if I draw a diagram, you can see, if I consider this as the nucleus, then there are certain clouds of negative charges that are revolving around the nucleus. These are various energy levels. Okay, these are various energy levels, right, where the electron resides, where the electrons are revolving. The electrons are revolving like this, okay, in various orbits. Now, what we have done is we have represented the energy levels as, we consider this as the first energy level, this as the second energy level, and this as the third energy level, and it continues, fourth energy level, fifth energy level, and so on. Similarly, as we know that Bohr suggested these energy levels as shells, we are representing the shells as various letters, are representing them by, so the first shell is K shell, second shell is L shell, next is M, another one it will be N, it will be O, and so on. So the number of shells are represented by the letters K, L, M, N, O, and so on, right? Now there are some limitations as to how many electrons a particular shell can accommodate, right? So there is a rule called Bohr-Bury rule. Now, what does this Bohr-Bury rule suggest? This suggests that the maximum number of electrons that a shell can accommodate is equal to 2n square. This is a term 2n square, where n is the number of energy level, okay, the particular energy level, right? So what the Bohr-Bury rule suggested, Bohr-Bury rule, this suggested that the maximum number of electrons that a shell can accommodate is equal to how much? 2n square, 2n square. So this was the expression. Now for first shell, what will be the value of n? The value of n will be equal to 1. And for first shell, the maximum number of electrons will be how much? 2 into 1 square. That means 2. So we can say that the first shell will accommodate a maximum of 2 electrons. That means you cannot insert more than 2 electrons in the first shell, that is in the K shell, right? The maximum number of electrons will be 2 for K shell. Understood? Similarly, if I consider the second shell, what will be the value of n? N will be 2. And for 2, the maximum number of electrons will be 2 into n square. N is 2 here. So 2 into 2 square means 2 into 4, that is 8. So we can say that the second shell, that is the L shell, will accommodate a maximum of 8 electrons, not more than that, right? For the third shell, you can also say for the third shell or energy level. Okay, these are all energy levels, right? These are all energy levels. So you can also call these as energy levels. So for third energy level, we have the value of n as 3. So 2 into 3 square equal to 18. Okay. So various energy levels have various accommodation of electrons, and this was in accordance with the Bohr-Bury rule, right? Now we know we have represented the energy levels into various shells. For first energy level, the shell is K shell, and for the maximum number of electrons that a K shell have is equal to 2. For second energy level, that is the L shell, the maximum number of electrons will be how much? 8. Similarly, third energy level, that is the M shell, it will accommodate a maximum of 18 electrons. These are the number of electrons. And for fourth energy level, that is for N shell, it will accommodate a maximum of 32 electrons. 2 into 4 square, that means 32 electrons. So in this way, you can accommodate the number of electrons in a particular shell, that is in K shell, in L shell, in M shell, and so on. Okay. Now if I tell you to write the electronic configuration of, suppose, magnesium, you have to write the electronic configuration of magnesium. Okay. So for magnesium, we know the atomic number of magnesium is how much? 12. So now we have to arrange 12 electrons. We know atomic number is equal to the number of electrons. So we have to arrange the number of electrons according to the number of shells. So if I write K, L, M, N, O, and so on, the number of shells, the shell numbers, we have to arrange these 12 electrons in these shells, right? So we all know that the first shell, that is the K shell, will accommodate how much electrons? A maximum of 2 electrons. So we have to write 2 here. Fine. In the second shell, that is L shell, how many electrons will be there? A maximum, there will be 8 electrons. You cannot fill more than 8 electrons. So I have to write 8 electrons here. So 2 plus 8 is equal to 10, and 2 more electrons are present. So I will fill the next 2 electrons in the M shell. So my configuration for magnesium will be 282. 282 is my electronic configuration for magnesium. Okay. Now if I say for phosphorus, say phosphorus, atomic number of phosphorus is 15. So I have to arrange these 15 electrons in the respective shells. So again you see, K shell will accommodate a maximum of 2 electrons. So I will write 2 electrons here. Similarly, L shell will accommodate a maximum of 8 electrons. So I will again write 8 here. Now how many electrons are left? 15 minus 10, that is 5 electrons are still there to be filled. Now what I will do is, the maximum number of electrons that M shell can accommodate is 18. So it can easily accommodate the remaining 5 electrons here. So I am putting the 5 in the M shell. That means the M shell will accommodate 5 electrons. So my configuration for phosphorus is 285. Understood? Now you have to make a table, which I am preparing it for you. You have to know the electronic configurations of first 20 elements, right? So electronic configuration of first 20 elements. You have to know the electronic configuration of first 20 elements. So I am making a table: element, symbol, atomic number. Now I am writing here electronic configuration, and under this I am dividing it into K, L, M, N, O shells, right? These are the shells, the shell numbers, right? So at first I am writing the first 20 elements. You have to memorize the first 20 elements of the periodic table, right? That is 1 to 20. Now I am writing this. The first one is hydrogen. We all know hydrogen. Its symbol is H. Next is helium. Helium is He. Next is lithium. You have to memorize all the 20 elements, okay? Beryllium. Next is boron, carbon, nitrogen, oxygen, fluorine, neon, argon, neon. Then we will go to sodium, Na, magnesium. Okay, so as there is no space left here, so I will just rub them and write the next few elements. Okay, magnesium is Mg. Magnesium is Mg. So now hydrogen atomic number is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Now I have to write down the electronic configuration. So you can see K shell can accommodate a maximum of 2 electrons. So hydrogen atomic number is 1. That means it has 1 electrons. So K shell will accommodate this 1 electrons. Right. So electronic configuration will be 1. That is, the electron will be present in the K shell. Similarly, for helium, you can see atomic number is 2. That means the number of electrons here is 2. So K shell will accommodate these 2 electrons. So hence its electronic configuration remains 2. Now for lithium, lithium has an atomic number of 3. Now from 3, K shell will accommodate a maximum of 2 electrons. I can't write 3 underneath this K shell. Why? Because the maximum capacity of K shell is 2 electrons. As there are 3 electrons, so what I will do is I will put 2 here and the remaining 1 electron will go in the L shell. So the configuration of lithium is 2, 1. Okay. Similarly for beryllium, it will be 2, 2 followed by boron. How much it will be? It will be 2, 3, 2, 4, 2, 5, 2, 6, 2, 7 and 2, 8. Now you have to stop here. Now if I write 2, 9 in case of sodium, it will be wrong. Why? Because you can see the maximum capacity that L shell can hold is 8 electrons. Here I have written 9 electrons. So it is not possible for L shell to accommodate a total number of 9 electrons. So what I have to do is I have to put 8 electrons here and the remaining 1 electron in the M shell. So the electronic configuration for sodium is 2, 8, 1. Understood? Similarly for magnesium, it will be how much? 2, 8, 2. So for magnesium, the electronic configuration will be 2, 8, 2. I'm just rubbing the upper portions so as to complete the 20 elements, right? Okay, number 13 is aluminium. Aluminium, silicon, phosphorus, sulfur, chlorine, argon, and the last two is potassium and calcium. The last two is potassium and calcium, right? Symbols are Al, Si, P, S, Cl, argon Ar, potassium is K, calcium is Ca. Now the atomic numbers are 13, 14, 15, 16, 17, 18, 19 and 20. You have to remember these 20 elements and their electronic configurations. Okay. Now aluminium will be how much? 283. For silicon it will be 284, followed by phosphorus, that is 285, 286, 287, 288. Okay. M shell, the argon has electronic configuration of 288. Now a question might arise. I am writing the correct configuration first. Okay, 2881. Okay, this will be the configuration of potassium, and calcium will be 2882. Now you may ask me, sir, why it is written as 2881? We know that M shell can accommodate a maximum of what? 18 electrons. So I might have easily written 289 here, as it can easily accommodate 9 electrons. But in reality, this case does not happen. The correct electronic configuration for potassium and calcium is 2881 and 2882. Okay. Now there is a concept called orbitals. That means orbits are further divided into orbitals. Due to the concept of these orbitals, we are writing the configurations in this manner. Okay. It is not possible for me to explain you in class 9 about the concept of orbitals. Okay. You will study it in higher classes. Now, for now, you just have to know that the configurations will be like this, not 289 or 2810, right? So I think you have understood how to determine the electronic configurations. You just have to keep in mind about the Bohr-Bury rule, that is 2n square rule, that is how many electrons you can accommodate in a particular shell, right? Next we will move on to the valence electrons or the valency electrons. Okay. Okay, so we will discuss about the valence electrons. At first, we have to know what is the meaning of valence shell. Valence shell is the shell, I can say the outermost shell present in the atom of an element is called valence shell. And the electrons that are present in these outermost shell are known as the valence electrons. And these valence electrons decide the valency of an element, right? So, valence electrons are the outermost electrons of the atom of an element. Fine. Valence electrons, the outermost electrons of an atom of an element, right? Now a question arises as why the noble gas are inert in nature. That means why the noble gases do not participate in any chemical reactions, right? Now if you see helium, neon, argon, These all are inert gases. Fine, inert gases. Now, if you notice the electronic configuration, helium has electronic configuration of 2. Neon has the electronic configuration of 2, 8. Argon has 2, 8, 8. Krypton has an electronic configuration of 2, 8, 18, 8. And the rest of the inert gases also have this sort of a configuration. So you can see that the last shell contains 8 electrons. That is, the last shell consists 8 electrons, and this is a case of octet electrons. If the last shell of an atom consists of 8 electrons, we call them as octet electrons, and these atoms are very stable in nature. That means if the last shell of an atom consists of 8 electrons, then they are considered to be very stable in nature, and as they are stable in nature, hence they do not participate in any chemical reactions. Thus we can say that the inert gases are the noble gases are inert in nature. Okay, but helium contains 2 electrons in its outermost shell. Okay, here if the last shell of an atom consists 2 electrons, we call them duplet electrons. What? It is duplet. Now, as helium contains 2 electrons in their outermost shell, that is, it contains duplet electrons, hence helium atom is also very stable in nature, and hence it does not participate in any chemical reactions, right? So there is a tendency that all the atoms tend to obtain the nearest inert gas shell configuration. Why? In order to attain the stability, right? Now, how an atom can attain this inert gas shell configuration, right? Here we will discuss about how an atom can attain the nearest inert gas shell configuration. In this aspect, we will learn about valency. So, what is valency? Valency of an element is the combining capacity, that is, the electrons that will combine with another element, okay, in order to attain the nearest inert gas shell configuration, right? Now, in case of valency, there are 2 types of valency. One is electrovalency. Electrovalency. In case of electrovalency, an atom loses or gains electrons in order to attain its nearest inert gas shell configuration. That is called electrovalency, right? Now, I am giving a relation between valency and the number of valence electrons. For metals, valency is equal to number of valence electrons. Okay, this is the relation. And for non-metals, valency is equal to 8 minus number of valence electrons. Okay, so this is the relation between valency and the valence electrons. For metals, the valency of an element is equal to the number of valence electrons, and for non-metals it is equal to 8 minus number of valence electrons. So how to prove this relation? We have few examples. Let's discuss some examples. Fine. Suppose if I consider sodium. Now sodium is a metal. Its atomic number is 11, right? We write it as Na1123. This is the mass number and this is atomic number, right? So if I write the electronic configuration of sodium, how will I write? I'll write it as 281. Now see, the outermost shell of sodium contains 1 electrons. See, this is the outermost electron. So in order to attain the nearest inert gas configuration, what will it do? It will tend to lose this electron. That means it will tend to lose these electrons and become 2,8. And I have told you that if the last outermost shell contains 8 electrons, then that atom or that ion is very stable in nature. So as it loses 1 electron, it becomes Na plus, right? And it is equivalent to neon, the configuration of neon, right? Neon has 2,8, the configuration. As neon is also stable, we can say sodium has a tendency to lose 1 electron in order to attain the nearest stable inert gas configuration. Thus, we can conclude that the valency of sodium is 1, right? As in case of metal, valency is equal to number of valence electrons. Hence, we can conclude that as sodium has 1 valence electrons, its valency is 1, right? Now, for magnesium 12, we can write it as 282. So what will it do? It will tend to lose 2 electrons. So if it lose minus 2 electrons, that means 2 electrons it tends to lose, it will form 2,8. So what will it form? Mg2 plus. Okay, so we can say that the valency of magnesium is equal to 2. So in this way, you can find out the valency of any metal. Now for non-metals, suppose I am giving an example. Nitrogen atomic number is 7. So if I write the electronic configuration, it will be how much? 2, 5. Now in order to attain the nearest inert gas configuration, that is 2,8, what will it do? It will have to gain 3 electrons in order so that it can reach its inert gas shell configuration. Thus we can say that the valency of nitrogen is equal to 3, or we can derive also, we can get the valency by the relation, that is valency equal to, for non-metals it was how much? 8 minus number of valence electrons. So for nitrogen the valence electron is 5, so 8 minus 5 will give you 3. Okay, another example I am discussing, that is oxygen. Oxygen has O16 8, right? So if I write its electronic configuration 2 6, now to obtain the inert gas configuration of 2 8, what will oxygen have to do? It will have to gain 2 electrons in order to achieve this configuration. So we can say that valency of oxygen is equal to 2. And we can again find its valency by this relation, that is valency equal to 8 minus number of valence electrons for oxygen is 6, so 8 minus 6 will give you 2. So in this way we can find the valency of different elements. For metals it will be equal to the number of valence electrons, and for non-metals it will be 8 minus number of valence electrons. Clear? Next we have to discuss about covalency. The second type of valency, that is covalency. Now covalency, what do you mean by covalency? Covalency basically deals with sharing of electrons by an atom of an element in order to attain the nearest inert gas shell configuration. This is the actual definition or the main function of covalency, that is it forms covalent compounds by sharing of electrons, right? That is, it does not involve any gaining or losing of electrons. Here you have to share the electrons in order to obtain the nearest inert gas configuration. Let's take an example. Suppose hydrogen. Hydrogen has 1 electrons, right? So if I write here hydrogen has 1 electrons, I am symbolizing it as this. Now, what will it do in order to attain the nearest inert gas configuration, that is 2? What it needs to do? It can share its electron to another hydrogen atom which is also having 1 electron. So in this way, these 2 electrons are bonded. That means this atom shares its electrons to this atom, and same is the case for this. So mutual sharing between the electrons of 2 atoms of the element will give you a covalent bond, and as a result the bond will be formed like this, and this is equal to H2, right? Similarly, if I take an example of, say, oxygen, the number of outermost electrons for oxygen is 6. So again, I can mention it like this, right? So we know the valency of oxygen was 2, so it has to share 2 electrons in order to attain the nearest inert gas configuration. So what will it do? It will share 2 electrons with another oxygen atom. Thus, you can see the total number of electrons after sharing will be 1, 2, 3, 4, 5, 6, 7, 8 for this oxygen atom, and same will be in the case of this oxygen atom also. That means they are sharing electrons to attain the nearest inert gas configuration, right? So in this way, the 2 oxygen molecules are bonded. As a result, they form oxygen molecule. So in this way, covalent compounds are formed. Fine. The last 2 topics that I will discuss is the isotopes and isobars. Now, what are isotopes? Isotopes, basically, isotopes. What do you mean by isotopes? Isotopes are atoms having same atomic number but different mass number. Right? That means they have different mass number but their atomic number remains same. For example, if I write the isotopes of hydrogen, what are they? They are H11, H21, H31. The name of this isotope is tritium, this is deuterium, and this is protium. Now you can see the atomic number remains the same, that is 1, but the mass number is different for the 3 cases. For first case it is 1, for second case it is 2, and the third case it is 3. Similarly, for chlorine, the isotopes of chlorine are Cl3517, Cl3717. For bromine it is okay, for oxygen I am writing 16,8, oxygen 17,8, and oxygen 18,8, right? And again I am writing bromine 79,35, bromine 81,35. So in every case, each case you can see that the atomic number remains same but the mass number is different. Fine. So these are isotopes. These are the different types of isotopes, right? And you have to know the isotopes of a particular element have similar chemical properties. The physical properties might be different, but they all have the same type of chemical properties. Okay. The last topic that I will discuss is the isobars. Now, what are isobars? Isobars. Isobars are the atoms having same mass number but different atomic number. Okay, atoms that have the same mass number but different atomic number, we call them as isobars. For example, you can say calcium 4020 and argon 4018, right? Now you can see calcium also has the mass number of 40, and similarly argon has also 40. The mass number of argon is 40, but the atomic number is different. That is, for calcium it is equal to 20 and for argon it is 18, right? So these two topics are important and question might come in definition forms. Okay, so what do you mean by isotope, isobars? Give two examples like this. So today we have completed this chapter. In the next class we will discuss some questions, important questions regarding this chapter, right? So we will meet in the next year as 2020 comes to an end. Hope new year brings new rays of hope in our lives. Okay, so wish you a Merry Christmas and a very Happy New Year in advance. Stay safe and try to enjoy in your home with your families. Thank you so much for watching.